So cumulative frequency distribution, density distribution, also known as CDF, you can just denote it with CDF, has similar concept as cumulative frequency distribution. We apply, if you remember, we apply cumulative frequency distribution when we make frequency distributions, and we use CDF when we are dealing with probabilities. So we usually add up first class in frequency distribution. We were usually adding up first class frequency into second class frequency, and last frequency gives us actually the sum of all frequencies, which is n in terms of frequency distribution. In cumulative density function, we're gonna use the same concept, and we're gonna add up previous probability in current. So we can say that fx, this one is really important. So we can say that fx equals probability of x less than equal to small x. Why? Because it's non-decreasing function. So here in our example, we have had number of heads and their probabilities, right? So we can have how to draw this x, which is number of heads, and its probability. So 0, 1, 2, 3. So there are three times when we can have maximum heads, 3 heads, and it was probability was 1 by 3, 3 by 8. Sorry, it's 8. 3 by 8, 1 by 8. So in normal way, when we draw the probability distribution, so we can have 0, 1, 2, 3. So this is our x, number of heads. And here we have probability, function of x, or probability of x, or you can say y. So it will be 1 by 8, 3 by 8, 3 by 8, and 1 by 8. Right? Here, same 1 by 8, or 1, you can say. So we have different points. And third one is 1 by 8 again. So we can say from 0, we can draw this one. Something like that. If you put like 3 by 8 exact value. Let me make it more clearly. 1 by 8. This is 3 by 8. So we know 0, 1, 2, 3. So at 0 is this point. At 1 it's this point. At 2 it's this point. At 3 is this point. So this is gonna be a probability distribution in simple way. Now when we draw cumulative density function or cumulative distribution function, we can say in this way. Because we are going to add up now for a CDF. It's 0, 1, 2, 3, 4, and so on. It doesn't matter it's discrete or continuous. So first one is 1 by 8. Second one is 1 by 8 plus 3 by 8. Right? It's like 4 by 8, so it's 1 by 2. Third one is 1 by 2 plus 1 by 8 plus 3 by 8 plus 3 by 8. So it's 7 by 8, which is almost 9 point something. And the last one is altogether add, so it's 1, because we know that it should be less than 1. It cannot go greater than 1. So from 0 to 1, this is our cumulative distribution function. From 1 to 2, we have half probability distribution of cumulative probability distribution. From 2 to 3, we have this one. From 4 and onward, we have 1. So that's the graph of a cumulative distribution function. Now you are clear about this. I hope that you are clear with how to make a cumulative frequency distribution and how to make a probability mass function. So keep in mind that we have done a cumulative distribution function of a discrete random variable at the moment, not continuous random variable. We will see it later on. But this is in both way, it's gonna be same. Here it's gonna be continuous. Let's take an example. But before that, there are some properties that this cumulative distribution function must lie from 0 to 1 because it's adding up, and the last one is the sum of the probabilities, which is 1. So, and it's non-decreasing because it keep increasing, as we know. It keep increasing, right? So it's going upward. So it's a non-decreasing function. What does that mean, non-decreasing function? It means that from limit x tends to infinity, the function, the probability function tends to will be 0, and if it tends to positive, if x is greater and greater and greater, it's positive number, the probability will go to 1. We will see with an example. So these are the properties you should learn. Let's take a simple example, same example of coin. Flip the pair coin 3 times. X is number of heads, we already know. So probability of X, and sport is like 0, 1, 2, 3. So CDF is probability of X, which is less than the small x for each infinity. X lies between minus infinity to plus infinity. So have you understood this one? Cumulative distribution function. Now let's see an example. Here, this is an example. A day's production of 850. In a factory, there is a production of 850 parts containing 50 defective parts and remaining non-defective parts. So 2 parts are selected at random. How many? 2. So I will ask you, what is x here? 50 or 2? Without replacement. So once we picked it, we don't replace it. So a daily production of 850 parts contains 50 defective. Means 800 plus 50, right? Total parts. And from those 50, we select 2 parts randomly, which we don't replace. Let the random variable x equal to the number of defective parts, 50, in a simple. So here, in this case, we are only considering 2 parts, remember. Find the cumulative distribution function of x. How are we going to do that? It's in front of you, but can you understand this example? Let me explain. We know here x is defective part, so x can be possibly 0, 1, 2. Why I said x is 0, 1, 2? Anyway, because here it says x is equal to the number of defective parts in sample. Remember that we start from 0, but the first part is 0 when there's no defective part, right? That's 0, we know that. But upper limit is how many we are selecting and total number of defectives. So total number is 50, and we are selecting only 2 parts, only 2 products, right? So which one is anyone which is minimum, we just select that. So if we say that there are total 50 defective parts and we are selecting 100 part. So here in this case 50 will be, x will be from 0 to 50. So whichever have a smallest value, we consider that as an upper limit. So lower limit is 0 here, because here we're gonna 2 is minimum, 2 is less than 50, because total part we are selecting which is less than our x, which is defective part. So we consider only 0, 1, 2. So we can consider only 3 outcomes of x, 0, 1, 2. And we have written here, we're making a graph, we just do 0, 1, 2 and x. Now, what is the probability? Let's come to the probability first. The probability mass function is calculated as, what is the probability of x is 0? That the two parts which we have selected, nothing is defective part. So we know from 850, 800 are non-defective. So the probability of non-defective is a complementary. It's going to be first part is 800 by 850. That's first probability times multiplication rule. Second part, because we are not replacing it, so remaining effective parts are 799 from total parts of 849, from among 50 is defective and 799 is effective. So we have done this. So we calculate the probability, we just solve it, and we get 0.87. Similarly, the probability of 1 out of 2, 1 is defective. So because we are dealing with twice, yeah, so total is 2. So 2 times 800 by 850. That's 1. That's the probability of non-defective part times probability of effective parts. So now, because first we didn't replace, so total number is now, we say, like first is just like an example of a coin. In example of a coin, what did we do? One head, first 3 heads means no tail, or 3 tails means no head. Then 2 heads. So there is a possibility twice 800 by 850, because we are saying that at least 1 is defective. So we consider 1 being defective, because let's say first one is non-defective, so the other one is 50 by 849. Do you understand this? So the probability is 0.1211. Similarly, both are defective. Yeah. Then 50 by 850 times 49 by 849, and this is the probability. And then we can draw. So therefore, probability of 0 having no defective, having at least 1 defective, and having at least 2 defective parts, because we are selecting only 2 products overall, can be given this. So first 0 until first product, the probability is 0.86, and then we start from 1 to 2, then 2 to 3 onward we can go. So we can say, in short, that probability of cumulative frequency distribution or probability CDF density function is 0 if x is less than 0. X means non-defective part is less than 0. Yeah? If x is between 0 and 1, then the probability will be 88%. So there are 88% chances that our defective part having a probability less than 1 and greater than 0. And 0.997 is between 1 and 2. And 1 is 2 and greater, less than x. So this you understand, right? Cumulative frequency distribution or cumulative distribution function. Before going to expectations and variation and moments, just want to clear one concept on the board. If you have remembered, we have already done the conditional probability and some rules, some basic rules. So one concept we didn't touch last time was about the C entry. Now, if you see the whiteboard, Yeah, now you can see. Hmm. So I have drawn a contingency table of from one example. You can see it clearly, right? So this is like an example from the book. So here, there's like an intention of a resident of a household to purchase. Intention to purchase. So if there are total 1,000 residents, so one, it's a contingency table. You already know about this. So 200 people, 200 residents are having intention to purchase, and they did purchase it, any product you can say, like mobile phone, TV, car, or any product. So what is the possibility of the residents having planning to purchase and actually purchase is 200 by total 800. Similarly, like 200 people are having an intention to purchase, but 50 didn't purchase, so rest purchase, like 150 purchased and 50 didn't purchase. So this is no purchased, this is actually purchased, and this is no intention of purchasing from this sample side. And then they have like 300 and 700, 250. So total is 1,000, and that's a contingency table. Now, one way is to, if get the probabilities, is as I told you, to make a distribution table, right? And then calculate the probabilities, relative frequency, and then calculate the probabilities. Another simple way. So if the example is simple, then you can actually draw the tree diagram or decision tree. How to make the decision tree diagram? So let's taking a simple example, same example. We can say, so households are classified here whether to purchase, whether they purchase or plan to purchase, or they actually purchased any product. So how can we make a decision tree? It's an alternative to the table. This is the contingency table. So first one, we can draw this table and we can find out. So let me draw this table in a smaller volume so that P2P means plan to purchase, okay? And actually purchase AP and purchase. I just draw it and make it smaller, right? That's why. Yes, no, yes, no, total. So that's 200, 100, 300, 650, 700, sorry, 50 and 650, 700, and that's total 250, 750, and total is 100, 1000. So let's make a diagram. So here are you. Wait, I mean like household, set of household. Set of household. H household. Now they have two options. Which one? Either to purchase right? Sorry, plan to purchase. Mostly we do the decision tree when we are having sequential decisions. So first thing comes first. So household, because you always, why it's a sequential? Because first you plan to purchase and then you actually purchase. It's not that you didn't plan to purchase and you just purchase. That's not possible. So you have two options. Either you plan to purchase or you don't not plan to purchase. So in this case, let's say plan to purchase is an event A. So the probability of event A is how much? The data is given. So we can say the probability of A is 250 upon 1000. So plan to purchase, yes, 250. Total 1000. That's the probability of this. And then not plan to purchase is like A complement. Probability of A complement. We have done this. What is that? That's 750 out of 1. So it means 750 out of 1000 household, they decided not to even thinking of purchasing a car. But 250 says that, okay, we can buy a car. So they are thinking about this. Now, further, they have two options because we are only dealing a two-way table. So, but then the people who have planned to purchase, they actually purchase, there's another event, there is a sub-event, and don't actually purchase, not actually purchase. So the actually purchased, they are probability of, now B, this is B, event B, actually purchase. So how many are they? They are A and B. Right? So after solving A and B, it means who actually purchased, who didn't, 50 didn't purchase. So who actually purchased? At 200 by 1000. 200 by 1000. Not actually purchased, simple, you know that. Probability of A and B complement. That's 50 out of 1000. Similarly, you can do further. So not didn't plan to purchase, but they purchased. Didn't plan to purchase and they didn't purchase. So who actually purchased but didn't plan to purchase are probability of A complement and B, which is 100 by 1000. And probability of A complement and B complement is 650 out of 100,000. So sometimes we also make this decision tree and to get out the distribution. It's the same thing. It can go further in another example because this example we only took two attributes, that plan to purchase and not plan to purchase. We can also extend it. For example, one male and female, and then male doing job of manager and female doing job of the managers and clerks, we distribute into, and then further we can add up age. So male with manager jobs having age more than graduates or high school, depends, right? So then it can go further that people who are male, who are managers, and who are having high school or not high school. Then it goes further. If I prolong it, just take a simple example, another example, and then I will ask you one example. Let's say male, female. So you need to put number. Let's say they are like 800 male and 600 female, 700. So total is 1500 people. So from male, how many managers and clerks? So managers are 250 and 550 are the clerks. From female, maybe 350 managers and clerks, 450 in a company. And this managers with education of undergraduates, undergraduation, and not undergraduation or less than undergraduation or graduation. Generally clerks, under and less than under. So you can keep this the CNT further depends how do you define attributes. So that's how we make the decision tree. Oh, sorry, I didn't know that you cannot see that. Right, now you can see that. So this is another way of making the contingency table, and it's easier if you have a small scale distribution or not so many numbers. But if there are different attributes, multiple times of attributes and distribution, then it's better to make a contingency table and to extract the probabilities through that. Otherwise, it will get you will get confused, and you don't know. You will be confusing, especially if one is given by another probability. So this is for the smaller scale. That's for the bigger scale. You can also use this at a bigger scale, but it's like not so suggestive. Means I cannot suggest you to do this with more than one attributes. So do you understand? Do you understand this decision tree? Yes?
Yes.
Hmm?
Hmm?
Do you understand or not? Okay. Okay, good. So only two people they understood. Rest they are. Oh, I thought maybe only few people are here. So it's a full class. Hope that I'm not making you sleepy in the morning, okay? So let's, if you understood, let me ask you one question. So you can draw, let's say there's another example. The one who have, can you make a probability distribution from the decision tree, not from the table, from the decision, as what I did it right now in this example. So there are, how many of them are like refreshing? So there are few numbers which are fast, three attributes, or two attributes, I think. People who can write faster and standard slower. And who can also write exams yes and no and total. So students who can have two attributes. One, they can write faster or slower. I'm just taking the example. And students who can solve the exams. Example, just an example. So let's say there are 42 students who can solve the exam faster, and there are 38 students who can't solve the exam faster. So total 80. Then there are students who can solve the exam but slower, and that's like let's say 70, and who can solve, and that's 150. So total 220, 108. So you have this information. Draw the tree diagram or decision tree and tell me the probabilities. Just tell me quickly the probability of what is the probability of A? Probability of A means who can solve it faster. So first thing, it's faster and slower. Then yes or no. Then yes or no. All right. So what is the probability of faster? A. Tell me. What is the probability of faster? I can make it diagram. Then maybe you can know. So students write faster, slower. How many? 220, 80. Right? And how many? Exam, yes or no? Right? And cannot write? No. As like 38 and 42, let's example. And this one is yes or no again, 70 and 150. Now, can you tell me the probability of A? Can you tell me probability of A and B? Oh, okay, tell me only this one. These two probabilities quickly. What is the probability of A? And then also probability of who can write faster the exams, given that they are faster. Oh, you cannot see? Wait, let me move. Oh yeah, that's too small. Sorry, my bad. Now you can see. Here you go. So I already have replies. 80 by 300. So yeah, that's 80 by 300. And here, what's the probability here? A and B. And then tell me what is the probability of, what is B? B is writing an exam. Given that they are faster. So you have to calculate this one as well. What is this one? Tell me. Who can tell me? Quickly. It's easy. That's why, because decision tree, you can just calculate it like from the tree. You have observations and you make a tree, and then you can calculate the probabilities. It's easier. So 80 by 300 is this one, probability of A. What is the probability that the students are faster and they can write the exam faster? Come on. 38 by 300, that's right. Okay, now quickly, which is this one? Probability of writing an exam given that the student is faster. See, it's a conditional probability. Just want to know that if you can do it or not. No. Why 68 by 80? Look, what is the probability of writing an exam? Because this one is writing an exam here with the faster. So there are total 80 faster, from which the 38 can write exam. So we have to know the probability of A and B. In conditional, we can say probability of A and B by given that A is always intersection by probability of B. Am I right? Oh, sorry, probability of A. This one. So in this case, this is the probability of A and B. So which is 38 by 300 upon, and probability of A is 80 by 300. So 300, it's like 38 by 80. So that's gonna be the probability of writing an exam and given that faster. Do you understand now? Yeah, if you solve it, it's like 0.475, almost, right? Something like that. That's perfect. Thank you. You are really aware of it. Now let's go back to the slides. So that's the decision tree, right? You can calculate any kind of probability by using the decision tree. Okay. So we have still time left, so we will try to finish what we have started. So we have done this. Yeah, we have done this. So let's go. Now let's see the expectation and variation. You know what is expectation? Expectation means average, mean. We can also call it mean of a random variable. It's denoted by, actually mu is not this one, it's E of x. And it's if x is discrete with probability mass function and support x1, x2, xn, these are the series number, then expected value, this is E, is sum of x px. That's gonna be the mean. So we will have x let's take example. Let's solve an example. Same example. Let's do the same example. Okay. So here we have x, which is number of heads in our example. So that is 0, 1, 2, 3. Probability of x, small x, which is 1 by 3, 1 by 8, 3, oops, why this is like 3 by 8, 3 by 8, and 1 by 8. Oh, he's giving me date. So what can I do? If you have this kind of problem anytime, just go to the format cell, and change into numbers. And it will, huh? No, not numbers. Format cell, where is format cell, and general. So now I write 1 by 3. Wow. Why is not giving me? Okay, I can solve it. 1 by 8. Oof. Format cell. Yeah, that's number. We need a normal number, right? Yeah, so if you add up, it will give me 1. See, 1. So now we have this one. We know this. And we have to now calculate the probability distribution. Where is that one? Yeah, this one. So this is x and then times px. So equal this times this. Seriously, it's taking too much time. So it's gonna be 0. I will just solve it. So this 0.38, 0.75, 0.38. So what is the mean expected value of x equal to sum of x px? 1.5. So mean expected value of x gonna be 1.5. Now let's see if we are true or not. So what is the average of 1.5? See, if we calculate average with that, it's also 1.5. And if we have expected value with the probability distribution, it's also 1.5. So now I think you understood it, that what does this mean, right? So this is probability mean. And then we have this example as we did it, which is 3.2 again in Excel. We have already done it. So recall variance. So variance is x minus mu square. So it's like expected value of x square minus mu square. What is mu? Mu is the difference. So what is expected value of x square is 0 square by 1.2. And since mu is the difference is 1.3, so why, look, this is the mean, mu, which is 3 by 2, and we have to calculate ex square. So for that, you need to do with the probability is 0 square with 1 square probability. And let's see how to do that in Excel. So now we have to do e square. Variance effects. So we will take this time this, and then we will multiply it with the probability star. Just instead of squaring, I'm just doing that. Okay, so right. So that's how we do that. And if we calculate it, it's 3. So 3 minus 1.5. So change is also 1.5. So 1 square by 3 by 8, 2 square by 3 by 8. 3 square by 9 by 8. It's 3. What did we get? Yeah, we get 3 as well. So since it's 1.5, mu is 1.5, so sigma square is equal to 3 minus 3 by square, which is this, 3 by 4, right? Variance of x equal to 3 minus mu square. So the difference, the mean expected. So mu is 1.5. We know that. We have calculated that. And expected value of x is 1.5 as well. So what's the difference? Difference is 1.5. So we can just solve it as 1.5 times 1.5. 0.75. And it's also 0.75. So now these are the definitions how to derive variance. So variance of x is x minus mu. So that's what exactly we do. This is mean, right? So the variation from mean of 1 point, because mean we say it's representing just 1 minute, and we will finish soon. So variance, we know that it's a change from the deviation, which is x bar, and here x bar is a mean. We have all calculated it, so it's a definitional formula. Solve it, a square minus 2ab plus b square f of x, and then times open it, and then you will find this one. And then finally you can get this one, and you can get this one. That's how we get it. Is a computational formula. That's how we compute the way we did it. So these are the properties that variance of x is always greater than equal to 0, because this is a variance and it's a square. So square of cannot be negative, right? And variance of x is negative because some are positive values, some are negative values. So our all positive error cancel out negative error. So we say it's always 0 if x is constant with probability 1. For all constant a, b belongs to any range, variance of ax plus b is a squared. So these are some key points, and kth central moment is this one. This we will talk later on in next week. Yeah, and after that we will have quiz. Okay, so far this is it.